What if light, the one thing we thought helped us understand the universe, was actually hiding one of its deepest music secrets? For decades, scientists have created entangled photons in laboratories, measured them with advanced instruments, and used them as the foundation for some of the most important experiments in quantum physics. Yet, hidden inside this familiar quantum light was a structure so complex, music, that it stretches across 48 dimensions and contains more than 17,000 distinct topological signatures. This was not found near a black hole, music inside a distant galaxy, or at the edge of the observable universe, but within the music, very kind of light scientists have been working with for years, which makes the discovery even more unsettling because the tools music to reveal it were already there. The problem was not that humanity lacked the technology. Music, the problem was that nobody knew where to look. And now this hidden architecture music inside light may force us to rethink what light really is, how quantum information can be stored, and whether the universe music itself is far more layered, coded, and mathematically alive than we ever imagined. To understand music, why this discovery matters, we have to begin with entangled light. Because although light feels ordinary in daily life, glowing from screens, reflecting from mirrors, and pouring from the sun, at the quantum level, it behaves like something far stranger than simple brightness moving through space. Entangled photons are pairs of light particles that remain connected through a mysterious quantum relationship, almost as if they were music, two separate notes from the same invisible melody, traveling in different directions while music, still belonging to one deeper system that ordinary physics cannot fully explain. Scientists commonly create these photons by sending a laser through a music special crystal, producing pairs of linked particles that can be used in quantum experiments, communication systems, music, and the future architecture of quantum computing. But what nobody expected music was that one property of these photons would open the door to something far larger. That property is called music orbital angular momentum, which describes the way light can twist as it moves, almost like a spiral or corkscrew made of pure energy. And inside that twist, researchers' music found hidden topological patterns that were not small, simple, or random, but part of a vast mathematical music structure reaching into 48 dimensions. It was as if scientists had been looking at a beam of light, as though it were a single music sentence, only to realize that beneath it was an entire invisible library written in a language no one had learned to read. The most astonishing part music of this discovery is not only that a 48-dimensional structure exists inside entangled light, but that this structure contains more than 17,000 unique topological signatures, each one acting like a different mark, symbol, or hidden pattern within the quantum behavior of light. Topology is a branch of mathematics that studies music properties that remain stable even when shapes are stretched, bent, or distorted, which means these signatures are not fragile decorations inside the photon structure, but deeper geometric features that may survive disturbances better than ordinary quantum information. That matters because quantum systems' music are famously delicate. A small amount of noise, heat, or interference can disrupt them, almost like trying to carry a candle through a storm, without letting the flame go out. And this fragility is one of the great obstacles standing between today's experiments and tomorrow's music quantum technologies. But if information can be encoded into topological structures inside light, then quantum communication and quantum computing may gain access to a more stable foundation because topology protects information through geometry, music, rather than relying only on fragile states that collapse easily. In simple terms, light may contain its own hidden alphabet for storing quantum information, and that alphabet music was not artificially invented by engineers, but discovered inside the natural twisting structure of entangled photons. When we hear the phrase 48 dimensions, it immediately sounds music, like science fiction, because human beings are used to thinking in 3 dimensions of space, with height, width, and depth shaping almost everything we can see, touch, and imagine. But in quantum physics, dimensions do not always mean physical directions music could walk through, because they can also describe the mathematical space needed to represent all the possible states and hidden relationships inside a quantum system. So this discovery does not mean scientists found a literal doorway where a person could step into dimension number 48. But it does mean that the structure inside entangled music light is so rich and complex that it requires a 48-dimensional mathematical description to fully understand what is happening. That is still extraordinary because it suggests that something as familiar as light can carry layers of organization far beyond normal perception. Music, almost like a flat-looking painting that secretly contains a three-dimensional music sculpture folded behind the canvas. For centuries, light has helped humanity decode the universe by revealing music, the composition of stars, the movement of galaxies, and the history of cosmic music expansion. But now, light itself has become the mystery because it may not only reveal information about reality, but also contain hidden structures of information, music within itself. The practical consequences of this discovery could be enormous, because if scientists learn how to control music, these topological signatures, they may be able to use them as a new way of encoding, protecting, and transmitting quantum information through light. Quantum computers need reliable ways to process information. Quantum networks need secure ways to transmit it, and future communication systems may depend music on structures that can resist noise, instability, and environmental interference better than the fragile quantum states used today. This is why the discovery feels like more than a beautiful mathematical surprise.